Hello. In this video lecture, I will be covering Chapter 25 for Module 4. The title of the chapter is the electric potential. The word potential here means two things for this as far as electrostatics are concerned. Sometimes we mean potential energy, like the concept that you studied back in mechanics. And we have something else called the electric potential, or the potential difference, or even a third word, the voltage. Okay, so there are two meanings to it, either energy or it is voltage, and we're going to cover both of them. But the bulk of the chapter talks about solving problems using the concept of conservation of energy. Up to this point, we have been using Coulomb's law, more or less, to solve problems where you are looking at the forces between the charges, and then you would calculate say the speed or the time it takes the object to reach a certain destination, whatever. In this chapter, we kind of deal with similar problems, but we will be using the concept of conservation of energy, something that you have studied back in mechanics. But I'm going to go over it for a few minutes, just kind of give you a quick brush up on what is the conservation of energy is all about, and then we will apply all of that to our topic. Okay. So, from mechanics, you've studied what is called the conservation of energy. Whoops, this is in pink. Let me change it. The conservation of energy. Now, the term total, we have what is called the total energy, E, is equal to K plus U, where K here is the kinetic energy and U is the potential energy. Okay, probably the notation that you've studied could be K plus PE, and K is KE, I'm not sure. But basically, this is the notation that we will be using. The kinetic energy is, of course, 1/2 mv squared. And then you have the potential energy. The potential energy takes different forms, so we'll come back to it later. The total energy is capital E. As you know, capital E is also reserved for electric field, right? So I'm going to be using E sub T, and the T here means total, so that's total energy. So it's not the electric field. The electric field, I'm just going to be using basic E, okay? So that's basically the statement, the mathematical statement of the conservation of energy. Kinetic plus potential. Let me give you a quick example. Let's say, for example, I am on at some height, and the height, let's call it H. And let's say I have a stone, and I throw the stone. I'm holding the stone between my fingers, for example, and I drop the stone to the ground. The question is, if the stone started from rest, okay, I want to know what is the speed of the stone just before it hit the ground. Okay, just before it hit the ground. Well, how do I do it? Well, one way to do it is use kinematics, free fall kinematics. As we know, the acceleration due to gravity is g. So I can use maybe, let's see, I can use the second kinematic equation, v squared equals v naught squared minus 2gy, y being the height, and v naught is the initial velocity. So we have the height h here, and it is in the negative because it is below, here is our datum right there, x and y. So that's in the negative y direction this way, so that's going to be negative. So this will become positive. So in this case, the velocity is equal to square root of 2g, and y here, of course, is the h. So there we go. I can find it by using the law of free fall kinematics, and I find the velocity of the stone just before it hit the ground. Now, this is all easy. Now, I can use also, another method is to use the conservation of energy, this one. Okay, how do I do that? Well, I asked the question, let me make the drawing again. So here is the height. Here is the stone, right? And I ask the question, what is the total energy of the object here? Well, it is K plus U, right? But because I'm holding it between my fingers, the kinetic energy is 0. So in this case, the total energy basically is U, which is mgh, right? Now, when the stone is right before it hit the ground, where the, let's say the height here is infinitesimal, is extremely tiny, all that energy that the object had here has been converted here into kinetic. In other words, the total energy right before it hit the ground, which is K plus U again, but this time, because there is no height, the potential energy, the gravitational potential energy is equal to 0, and all of it is 1/2 mv squared, right? Now, because of the conservation of energy, conservation means what? Means, go back to this formula, it means the sum of the kinetic plus the potential is always a constant. This E, this total energy E, okay? It's always a constant, same number all the time, okay, for a conserved system. In other words, those two values, this one and this one, must be equal because the total energy is conserved, okay? So now I'm going to equate them together. So I have here mgh must equal to 1/2 mv squared by the law of conservation of energy. The masses cancel out, and I can solve for v, and I would get square root of 2gh, which is, as you can see, the same as this one. You see that? So here I have two methods of solving the same problem. I can either use the kinematic equations, okay, free fall kinematics in this case, or I can use the conservation of energy, all right? Okay. So that's a little review. One more thing I want to talk about, and that is the potential energy, U. There are two versions for the potential energy, at least two versions that you have studied already. One is that when we're dealing with height, on the surface of the Earth, so the potential energy here is mgh, okay, where h, of course, is the height from the surface of the Earth, for example. And g here is the acceleration due to gravity, and the height must be, we assume that the height is small enough where g here does not vary, does not change, you see what I'm saying? So this equation is a very good equation when dealing with gravitational potential energies that are in the vicinity of the gravitating object, say the surface of the Earth or something like that. Now, in terrestrial mechanics, where the study of planets and stars and stuff, if I have, say, the Earth right here and the Sun right there, all right, and this is the mass of the Sun, big M, and the mass of the Earth is r, and let's say they're separated by a distance, small r, then there is also a gravitational potential energy. This gravitational potential energy is equal to the product of the two masses, okay, divided by their distance, okay, not squared, just by their distance, up to a constant, big G. We call it the universal gravitational constant, 6.67 times 10 to the negative 11. It's just a constant, right? And usually, because we are dealing with gravitation, and the nature of gravitation is attractive, this attraction, we put a minus sign beside it here. Maybe I should, like that, okay? So the minus sign indicates that the nature of this gravitational potential energy is attractive, which is always attractive for the case of gravitation, okay? So those are the two formulas that we deal with. Of course, you use the second formula here when we're dealing with big terrestrial objects and the distances are vast and so on. So this one becomes, it doesn't apply to this case, like I said, because the height here is assumed to be small enough where G here does not change. You see what I'm saying? Okay. So those are this is basically what we have studied. Now, I want to apply the same idea here for electrostatics. As a matter of fact, we have almost identical form for electrostatics. what I'm trying to say is the following. If I have, well, hold on, one more thing. Okay, so you may ask, how did you come up with this one? Okay. We know that the force, well, let's go back to work. Remember the work energy theorem. What's the definition of work? Well, work, you said F times X, right? How do we come up with it? Here is the mathematical expression for work. Work is equal to the integral of the force dx. Okay, from A to B. That's the formal definition of work. From the work energy theorem, we know that work is also equal to delta U is also equal to delta K. In other words, go back to the book and read about the work energy theorem. It's a very important theorem in mechanics. And it basically says that the work is not just Fx, or the integral of the force dx. It's also the difference between the potential energies, or the difference in kinetic energies. Maybe I'll elaborate just for 1 minute on that very quickly. Okay. For example, let's say I'm riding my bicycle. Okay, I'm riding my bike, and I am going with initial speed of, let's say, 3 meters per second, for example. Okay, now I push on the pedal, and now I have increased my speed to, say, 5 meters per second. Okay, so initially my kinetic energy, let's call it K naught, is 1/2 mv naught squared. Of course, m here being my mass and the mass of the bicycle. V naught is 3 squared, right? And then my new kinetic energy, the second one, is 1/2 m, my mass and the mass of the bicycle, times 5 squared, right? V squared. The difference between the two values, okay, the difference between them is also equal to the work, how much work I have done to increase my speed from 3 to 5. You got that? This is called the work energy theorem. So there are two ways to calculate work. I can either calculate directly if I know the force and the distance, or I can just say, well, the difference between the two kinetic energies. Okay, that's one way to do it. Here's another example. Let's say is the table, okay, and let's say there is a book standing on the table here, okay, and let's say there is a shelf here. So I hold the book and I move the book to this shelf, and I make it stand on this shelf. Okay, of course I have done work by lifting the book, by holding the book in my arm and lifting it upward against gravitational pull, and I put it on that shelf, on the top shelf, right? It has gone, of course, a distance, let's say h. Okay, now here's the table, there's the legs of the table. Let's say that I am measuring everything from the surface of the floor, the surface of the floor. So the initial height of the book, let's call it h1. Let me call the new height here h2. Okay, so initially here, where the book was standing on the table, the potential energy U1 was mgh1, right? M here being the mass of the book, g is acceleration due to gravity, and h1 is just the initial height of the book, right? Now I moved the book from here to here, so now the new potential energy is equal to mgh2, right? Obviously I have done work, and that work is equal to Fx. You see what I'm saying? Another way of saying it is that the work that I have done to move the book from the surface of the table to the shelf, to the top shelf or whatever, this work is also equal to the difference in potential energies. In other words, it is U2 minus U1. Okay? So here we have two formulas that calculate work. One is that delta K, the difference in kinetic energy like I showed you here in the bicycle example, or work is equal to delta U, and of course the one that we are familiar with is Fx, or the integral. Okay? All right. Now, like I said, we have similar situation in electrostatics. Let's say, for example, I have a capacitor. Let's say I have two plates here. Let's assume this is positive, this is negative. Okay? And let's say, for example, I have, suppose the separation distance between them, let's say d, okay? Whatever number you have. Suppose that I have a proton, and the proton initially is at the positive plate. In other words, it's somehow I'm holding it between my fingers, figuratively speaking. Okay? Then I'll let go. What's going to happen? Well, the proton is going to shoot toward the negative plate, like that, right? Do you see the analogy of this proton shooting to the negative plate and the stone falling here? The stone starting from here, I'm holding it between my fingers, I'll let go, the stone falls to the ground. It's the same analogy, guys, exactly the same analogy. So here I have a proton, and it shoots to the negative plate here, and the separation distance, so think of this d like the quote-unquote height, got it? Now, if I am given, let's say, the initial potential energy of the proton. So I know the initial potential energy of the proton, which is an electric potential energy. Okay? And I would like to know what is the speed of the electron right here. Okay? So I can, in this case, also use the conservation of energy. Remember, the conservation of energy law applies everywhere. So E sub T equals K plus U. So I want to apply this formula to before I release the proton here, and I want to apply it also right here just before the proton hit the plate, the negative plate. And then I can equate them together because energy is conserved. And with that, you know, I have K plus U. I can solve for the velocity eventually. You got that? Okay, so I'm going to give you a real example of this from the book. What I like about this chapter, as far as the textbook is concerned, he presents a really, really good example. They are one of the best I've ever seen. So I'm going to be doing a lot of, I'm going to be solving a lot of examples from the textbook from this chapter. I'll begin with example 21.5, which is pretty much similar to the problem that I'm talking about here. Let me go to it. And that's on section 1. So I can just scroll down. I should be able to see it. What? Oh, next page. Analog. Bear with me until I find it. There we go. Here, conservation of energy, example 25. It's a pretty simple example. There is a picture associated with it right here. Let's read it. He says a 2 by 2 centimeter, which is basically the area, parallel plate capacitor with 2 millimeters spacing is charged to plus or minus 1 nanocoulomb. So there we go. So you have the two plates here, positive and negative. They both charge to 1 nanocoulomb. This is the positive terminal. This is the negative terminal. And the distance between them is 2 millimeter in thickness, okay? And initially what I have a proton right in the middle of the way right here, and this is an electron. We're just going to solve it for the proton. Let's continue. He says, first a proton and then an electron are released from rest at the midpoint of the capacitor. Two questions here. What is each particle's energy? So I want to calculate the total energy. When you say energy, it means what is the total energy? You know, kinetic plus potential. And then he's asking, what is each particle's speed as it reaches the plate? In other words, just before it hit the plate, what is the speed? I'm just going to do it for the proton. I mean, they're both identical except the charge is negative and all that. So I'm just going to use it for the proton. All right. So what you have in here, let me make it a little bit bigger if I can. Oh, it is the maximum. It's always maximum. Anyway, so I have the proton right here. and I'll let go, and it's going to go to the negative plate, and he's asking me to calculate the speed here right before it hit the plate. Also, he's asking me what is the total energy of the proton. Okay, and remember, total energy doesn't matter where, here or in the middle, it doesn't matter, it's all the same. So all you need is just to get that value. You see what I'm saying? Okay, so before I do this problem, let's just brush up very quickly what I said. So we have the total energy is kinetic plus potential. Now for electrostatics, here is the gravitation, first of all. Gravitational. And that's electrostatic. Electrostatic. There we go. Okay, so we said that the potential energy is mgh. In electrostatic, the potential energy is q e d, or h or y or x, whatever. Okay, I think your book uses s, but anyway, I'm just going to use d. Okay, so do you see the analogy there? It's kind of easy to remember. The mass always analogous to the charge. The g here, you can think of it like you know, gravitational field, if you will. So this is electric field, and then you get the distance. Okay, there we go. And then we said that u between two masses, it's g m1 m2 over r, and there is a minus sign here. That's just details. Here we have similar thing, which is g q1 q2 over r. Okay, so we're going to be using those equations to do that. And of course, oh, the kinetic energy is always the same, so that's just 1/2 mv squared. This one again, same thing, 1/2, not qv squared, mv squared. Okay, so that's basically the analogy. You may want to write them down. And of course, the total energy apply to both. Okay, conservation of energy is a universal law. All right. All right. Now let's start with our example. So what I have here, let me make the drawing first. So I have here positive and negative plates. I guess this is the positive one. That's negative. Here's midway between them right here. Initially, I have a proton. I'm going to ignore the electron. You can do it yourself. Okay? And I'm going to let the electron go. And of course, the electron is going to go and hit the negative plate like that, right? And then he said the charge here, I'm going to make it capital Q for now, is equal to 1 nanocoulomb. And here the charge is -1 nanocoulomb. You got that? And that's the charge of the proton, which is E, right? The fundamental charge here is E. We already know that, which is 1.602 times 10 to the -19 coulomb, right? Okay. He's asking for, first question, what is the total energy? Okay. And the second question, what is the velocity of the proton just before it hit the negative plate? Okay. So I go back to those formulas right here. Okay, the one that fits me here, I don't look at this one. U equal, I'm sorry, it should be K, right? I bet you're screaming at me. That's not this K. Sorry, the electrostatic constant. There we go. Is that better? Okay. So so here, of course, you have two formulas here. This formula, the second one, guys, applies to the gravitational, excuse me, the electrostatic potential energy between two, say, point charges, Q1 and Q2, okay? This one, however, if you're given a field, okay, if you're given a field, you use this formula. Well, obviously, in this problem, we are given a field. We have an electric field going this way. See that? This is an electric field. So, obviously, we're going to use this formula right here. Okay. So, the total energy, well, as you can see right in midway here, at midway, the kinetic energy is 0. He said the proton started from rest. You see what I'm saying? Okay. So K is equal to 0. So the total energy, which is K plus U, the K here is 0. So I'm left basically with U, which is what? Q E D. Now, what is D? He said that separation distance between them is, I'm looking at my hard copy here, 2 millimeters, right? So midway right here, so the separation distance here is 1 millimeter. That's D right there. So here we have D is 10 to the negative 3 meters. Okay? That's the first thing. Remember, he wants the total energy. Okay, do I have Q? Yes, well, Q is just E, so I'm good to go here. So I got the Q, I have the D, now the E. He didn't give me the E. You see what I'm saying? If I go back to the picture, he didn't give me the E at all. Okay, he didn't say anything about it. Well, how do I find the E then? Again, we go back. We studied the electric field due to a capacitor, or a charged sheet, if you remember. We studied it several times, twice at least. Once in the chapter 23, when we were calculating electric field for a distribution of charge, and the second time when we covered Gauss's law. But if you may recall, the electric field due to a, again, I keep reviewing things. Here is the charge sheet. And the electric field due to it is, if you remember, sigma over 2 epsilon naught. Okay? Now, the 2 here indicates that the electric field is emanating from both sides. See what I'm saying? Okay. Now, if you have the capacitor, however, for this case, capacitors, their electric field is only emanating from one side, the other side is kind of insulated. So in this case, the electric field due to a capacitor, to capacitor plate, and I remember deriving that formula for you in one of the videos, I think Gauss's law, is sigma over epsilon naught. That's the electric field due to capacitor plate. You take that, you remove the 2, basically. Okay? All right. So here it is. So E here, remember, distinguish between E sub T, which is energy, total energy. E here, electric field. E here is sigma over epsilon. Well, he didn't tell me, epsilon naught, he didn't tell me what sigma is, but I know what the expression for sigma. Sigma is charge per area. And guess what? He gave me both. See that? He said the charge is 1 nanometer, nanocoulomb, and the area, well, he said in the problem, a 2 by 2 plate capacitor. So here I can find the area. So the area here is 2 times 2, which is 4 centimeters squared, or 4 times 10 to the negative 2 meters squared. There we go. I got the area. Okay. And then Q is given to me. So basically the total energy right there, this one right here, guys, the total energy becomes E Q over A epsilon naught times D. There we go. This is the full expression for the total energy. You got that? And all you need to do is just plug it in. So the fundamental charge, 1.602 times 10 to the negative 19, times 1 nano, 10 to the negative 9, distance, 10 to the negative 3, divided by the area is 4 times 10 to the negative 2, times epsilon naught, 8.85, times 10 to the negative 12, and then we just calculate that. Okay? I'm just going to get the answer from the book. He did it completely different. I'm looking at the hard copy. Anyway, he ended up getting 4.5 times 10 to the negative 17 joule. There we go. That's the total energy. I'm looking at my notes and see if I've done this problem. I don't think I have. Anyway, okay. And there we go. So he said, what is the total energy? There we go. I got it. Okay, is that clear? Okay, good. Now, the second part of the problem, he says, what is the velocity? Go back to the drawing. What is the velocity of the proton right here? Okay. So again, we use conservation of energy. We ask, what is the energy here? And what's the energy here? And we make them equal to each other, of course. Okay. So here we have use conservation of energy. So we have E total in midway here, let me just remind myself, equals E total at negative plate. Okay? So what's going on at the negative plate? Well, all that potential has been gone because the distance is what? How far? Here, let me show you the diagram again. When the proton is right here, what's the distance here between the plate and the proton just before it hit the ground? Before it hit the plate. Practically zero, infinitesimal distance. So for all practical purposes, it's zero. Well, what does that mean? It means since the potential, by its own nature, depends on distance, depends on height distance. Well, that distance is zero, so therefore there's no potential. The potential is gone. What happened to it? It has converted totally into kinetic. So all that potential that was here converted into kinetic over here. Got it? So I'm going to equate the potential here equal to the kinetic here. That's basically what I'm trying to do. So here we have, at midway, we already said that this is QED equal to 1/2 mv squared. I already calculated this value right here. That's the number right there, right? So I can go like this, 4.5 times 10 to the negative 17 equals to 1/2 times the mass of the proton, 1.67 times 10 to the negative 27, multiplied by the velocity squared, and then I can solve for the velocity. And when you work it out, again, I'm just going to copy the answer. He calculated it to be 2.3 times 10 to the 5th meters per second. And there we go. Got it? Okay, good. So now I hope you have an idea how this chapter is progressing. It's all about conservation of energy. Let me do one more. I have a couple of more before I go into the potential difference, which is the second topic in this chapter. All right. Example, actually 1, 2, 3 more. All right. Example 25.2. 25.2. I have two in a row, 25.2 and 25.3. They're both in a row. I'm going to do them both. There it is. Approaching a charged sphere. And there is a picture associated with it. He says, a proton is fired from far away. Okay, look at that word. Underline this word, far away. Why would he say something like that? A proton is fired from far away at 1 millimeter diameter glass sphere. This is kind of a more or less nanotechnology. So at 1 millimeter diameter glass sphere that has been charged to plus 100 nanocoulomb. What initial speed must the proton have to just reach the surface of the glass? In other words, it will reach the surface of the glass. It's not going to penetrate the surface of the glass. We don't want it to penetrate it. We want it to basically just get there and then rebound. How do I know it will rebound? Well, look at the charged sphere is positive. And the proton, of course, is positive. So when as the proton is approaching the sphere, it is the repulsion force is increasing. Eventually, it's going to stop. So what I'm doing here in the lab, I'm tweaking the speed to get just the right speed in such a way that I just want to have the proton to barely touch it. I'm sorry, I got a little noisy here. Let me close the window. Okay, let's see how we do that. Let me draw the picture for you. .2, and what I have here is the sphere right here, okay? And it is positively charged. And I have the proton far away, he said, and it being shot with some velocity v0 toward the sphere, right? From far away. So that means the distance is really, really far. Okay. I want to know what is that magic speed such that the electron, the proton, will just go right close to the surface right here and then rebound. Okay? Just touch it. I don't want it to penetrate the sphere or, whatever, or go through it, whatever. Okay? So how do I do that? Well, again, we use conservation of energy and ask the question, what is the total energy of the proton here? And what is the total energy of the proton here, as it touches the sphere? Those two total energies must be equal. You see what I'm saying? They must be equal. So, what is the total energy here? Well, we know that total energy is what? Let me just write it down again. Here is K plus U. Okay. Obviously, the proton has kinetic energy here because there is a speed v0. This one is usually very, very large speed. Does it have potential? Well, what does the potential depend on? Well, the potential depends on distance, remember? That's one thing. Second, this case is, remember we said there are two kinds of potentials. Where should I put it? I'll put it here. I don't want to clutter the page. But we said that is U equals QED. You use this formula when you have an electric field. You see what I'm saying? And if you have 2-point charges, you use K, Q1, Q2 over R. And this is the formula that we're going to be using for our case because basically I have two objects here, two charged objects. I have a proton and I have a 1 millimeter charged sphere, charged ball. See what I'm saying? So I can call the proton, I can call it E, and then I can call that big Q, for example. Call it whatever you like. Okay, so let's go back to our problem. He says the proton was shot from far away. What does that mean? It means the distance, R, is very, very, very large. Okay, so what is 1 over a very large number? Well, it becomes infinitesimal. It's small. So when he says a proton is fired from far away, what he's telling you, ignore the potential. The potential is negligible. It's so minute we don't even consider it. Got it? That's the meaning of far away. Got it? Okay. So in other words, the total energy here, far away, is nothing but, it's all kinetic. That's all. Okay? Now, when the proton is coming towards the sphere, it's decelerating. It's slowing down, slowing down, slowing down until it finally stopped. Where did it stop? It stopped at exactly the surface. Just barely licks the surface and then rebounds, right? So at the moment it stopped, what is its kinetic? 0. What happened to that kinetic? It converted all to potential. This one right here. So when the proton at the surface of the sphere, it's all potential. Those two must be equal. So that's 1/2 mv0 squared equals to the potential K E Q over R. Well, what is this R? Well, what is it? How far is the proton from the sphere? Well, they're touching each other, so how far is it? Go back to Newtonian physics. How do we measure distances? We measure distances between the center of points. You see what I'm saying? The center of mass. So here, you're measuring the distance between the proton and the sphere from the center of mass, right? From here to the center of mass of the proton. Of course, the proton is only roughly 1 femtometer in diameter, where this one is a whopping 1 millimeter. It's a huge object compared to the size of the proton. So for all practical purposes, we just take the radius of the sphere as the distance, okay? So I'm going to call that big R as a radius of the sphere, okay? And that's it. We're basically done with the problem. We said, what is I forgot what he wants. Yeah, what is the the velocity of the proton? So V naught in this case is going to be 2kEq over mr under the root, and there we go. We just calculate that. Instead of saying, okay, I'm going to leave it. I'll leave it for you to get that number. The number, I'm looking at my my textbook here, is 1.86 times 10 to the 7 meter per second. Okay, there we go. The next problem I want to do, like I said, I have a lot of problems, a lot of examples to go through. All of them have to do with the conservation of energy. So I'm trying to go through them and then hopefully have time to also do some problem from the homework. Example 25.3. The title of it is Escape Velocity, Escape Speed. Let me read it for you. It's the next one. Escape speed. He says an interaction between two elementary particles causes an electron and a positron. Positron is a positive electron, to be shot out back to back with equal speeds. Okay. What minimum speed must each have when they are 100 femtometer apart in order to escape each other? Okay? That sounds like a tough problem, doesn't it? Okay, a femto is 10 to the negative 15. Okay, that's not a big deal. Just a small number. It's a small unit that we use in nuclear physics and particle physics. So he said, what minimum speed must each have when they are 100 femtometer apart in order to escape each other? Now, what does it mean when we say escaping each other? Well, it has to do with escape velocity. So let me go over escape velocity from the physics, the mechanic course that you've taken. So let's have a quick review of escape speed. Say, for example, you have the Earth and the Sun. So the Earth goes around the Sun in an elliptical path, something like that. Here is the Sun, according to Kepler's second law and first law. The Sun is located at one of the foci, right? And let's say here is the Earth right here, and let's say it's moving in this fashion like that, around the Earth, around the Sun, like that. Okay? Now, what is the total energy of the Earth as it goes around the Sun? Okay? Now, the mass of the Sun is this. Mass of the Earth is that. So we know that the total energy, E, is equal to K plus U. As a matter of fact, it's actually minus U, because remember I talked to you about it? Minus has to do with the gravitational potential energy is attractive, so we put a minus sign there. It's not really, we're always subtracting the kinetic and the potential as absolute values, okay? All right. So that's basically the total energy of the Earth as it goes around the Sun. A little more details, basically it looks something like that. So this is E equals to 1/2 mass of the Earth, V squared, velocity squared at that instant, right? Minus G, mass of the Sun, mass of the Earth, divided by their distance, Sun-Earth, like that. That's basically the equation that describes the total energy of the Earth as it goes around the Sun. Okay? All right. Here is something interesting. Which one is greater, the kinetic or the potential? Or does it really depend on where the Earth is located? Here's what's happening. If it happens, let me just go back to this simple formula. E equals K minus U. If it happens that K is greater than U, okay? If the kinetic energy is greater than U, I'm talking here about the absolute value, okay? Ignore that minus sign you see in between. The absolute values, okay? No minus signs, just the magnitude. If the kinetic energy is greater than the potential energy, what will happen? The Earth is going to escape from the gravitational pull of the sun, like this. It's going to go like that, and it's going to go shh, and it's just going to go into space. In other words, it will not be in a bound orbit. So here it becomes orbit is unbound. Or what will happen is they're going to be the escape the gravitational pull. That's the meaning of when the kinetic is greater than the potential. However, in our case right now, as the Earth has been going around the sun for billions of years, why is it in a bound orbit? Because the gravitational pull of the Earth is greater than its own kinetic energy. Okay? So here we have a bound orbit. Orbit is that U is greater than K. Okay? You got that? Okay. So if it happens that the kinetic is greater than the potential, you will have an escape. Okay? Let me give you one more example. I know you're probably wondering, why do I talk about all of that? You'll see in a minute. Here's another example. Let's say I'm standing, I'm on the surface of the Earth. Just say I go outside in the park. Here I am. And I'm holding a stone, okay? And I throw the stone up in the air with some initial velocity v0. So what's going to happen to the stone? Well, it's going to go up, 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 and then it's going to fall back. It's going to fall back to the ground, correct? Now, if I hit it even higher, or harder, or faster, it's going to go even higher, and it's going to come back, and so on, okay? Here's the question. Would I be able to hit it with a certain speed such that the stone will escape the gravitational pull of the Earth? And the answer is yes. Here's what's happening. When you ask the question, why the stone comes back, okay, ignore the atmosphere. Let's assume there is no atmosphere on the Earth. Okay, let's say I'm on the moon and I throw a stone as hard as I can upward. Well, it's going to come back, okay? It may go higher than the Earth, but it's going to come back eventually. Well, why does it come back? For the same exact reason that we were arguing here. What happens is that here you have, as the stone is going up, the total energy of the stone is K plus U, where this U is greater than the kinetic energy. You see what I'm saying? The kinetic that I'm given, which is this related to the velocity. And that's why it comes back. Why? Because the stone is in a bound state, a gravitational state with the Earth. That's why it comes back. The Earth will pull it down. Okay? The only time that the stone is going to escape the gravitational pull of the Earth is that when I give it a kinetic energy that is greater than the bound state, than that bound potential energy. Okay? So when I ask the question, what is the minimum velocity that I could give the stone to make it escape the gravitational pull of the Earth? And that's when I say K, when it's just barely equal to the potential. And in this case, I have 1/2 mv0 squared is equal to G, mass of the stone, mass of the Earth, divided by the radius of the Earth, correct? And now when I calculate that, well, let me clean it up a little bit. And this velocity is basically 2G mass of the Earth over the radius of the Earth under the root. Famous equation in astronomy and space physics and rocket science. There we go. This is the escape velocity. If you would calculate that, you actually put the mass of the Earth, radius of the Earth, the G value, you will get something like 11.2 kilometer per second. Okay, of course, we're assuming no atmosphere. In other words, if I would take that stone and throw it up in the air with a speed of 11.2 kilometers per second, which is about 8 miles per second, it will escape the gravitational pull of the Earth. You got it? Okay. Now, just to give you a feel for that number, 11.2, so that's about what? 11,000 meters per second. The speed of sound is 330 meters per second, if I remember. So what's the Mach here? Let me calculate that. So 11,000 divided by 330, that's about Mach 33. Okay, so in other words, even if I have the most powerful bullet, a gun, and I shoot the bullet up in the air, it is bound to come back. So I have to shoot it with a minimum speed of Mach 33 to actually have it escape. Okay, all right, a long lecture about escape speed. Let's go back to our problem. I hope you're enjoying it. So what we have here, we have what is called a positronium. Let me just show you a picture how it looks like. I'll go to the next page. We have something called a positronium. Positronium is basically, it's a positron and an electron are formed. It's called pair production in quantum mechanics. And this pair production, so what will happen, they will start spinning about each other, about their center of mass right here. And then eventually they will live for something like 10 to the negative 27 seconds. And eventually they will annihilate each other, and they will shoot 2 gamma ray photons in opposite directions. Okay, so this is the negative electron, and this is the positive electron, positron and electron. You got it? So they will. So that's basically what we have in that situation. But what he says, if the positron and the electron are at a distance of 100 femtometer, a femto is 10 to the negative 15 meters. Okay. So if it is, if they are 100 femtometers, with what speed should they be going? With what speed should they be going in order for them to escape from each other? See, there is a tendency for them to come together because they're both positive and negative. What's the minimum speed for them to be going in the opposite direction to escape from each other? Well, again, we go back to that escape velocity. If you know the concept of escape velocity, what's the condition for escape velocity? It's when the kinetic and the potential are equal. See what I'm saying? So now, for the condition for them to escape from them at a minimum velocity, when the potential between the positron and the electron is equal to the kinetic energy. You can pause the video and think about that. Okay? So in other words, here we have the kinetic energy, so condition for escape is that when the kinetic energy of the positron plus the kinetic energy of the electron equals to the potential energy between them, for both, at 100 femtometer. Okay? Now remember, the positron and the electron are identical particles. The only difference, one is matter, the other one is antimatter. The only difference between them is the charge. So, and that's not a big deal. That's not something significant when it comes to kinetic energies. So in this case, I'm going to have 1/2 mv squared, v naught squared, for the positron. They both have the same mass, right? Plus 1/2 mv naught squared for the electron equals k e squared over what? The distance between them, which is 100 femto. I'm going to call it r for now. So this gives me mv naught squared equals to k e squared over r, and so therefore I can just solve for the escape velocity. This is the escape right here. V naught is equal to k e squared over mr under the root, and there we go. You just calculate that. You see what I'm saying? And when you calculate it, you can just plug in the numbers. Again, I'm just going to get it from the book. He got 5 times 10 to the power of 7 meters per second. Okay? Okay, good. One more problem. Example 25.4. That's the next page. Same section. Oops, back one page. There, should be here somewhere. That's the solution of the previous. There we go. Here. Oh, sorry. It's called launching an electron. Sorry, bear with me. There it is, right here. All right. So what you have here, a picture there, right there. I'm gonna let me read the problem and I'll draw the picture for you. It says 3 electrons are spaced 1 millimeter apart along a vertical line. Here they are. So I have electron 1, 2, and 3, and they are 1 millimeter apart. Okay. By the way, those problems that you read in the end of the chapter or example, these are real life problems. It's not like the author of the book sat down and just came up with them. They're really real life problems. They're coming out of scientific papers, and they're a little bit simplified. The numbers are a little bit modified to make them a little bit more friendlier, if you will. But these are real problems. A lot of them are real engineering problem or physics problem coming out of a lab. So take those problems really in the sense their data is pretty serious. I mean, when you get, for example, like we just solved the velocity of escape is 5 times 10 to the 7. If you go to a physics, nuclear physics lab and actually do this experiment, the velocity of escape of at 100 femtometer, it would be something compatible with that number. Not exactly this one, but it will be something compatible. So those numbers are real, really. They're real experimental numbers. So you take them kind of seriously. Okay, so here we have 3 electrons are spaced 1 millimeter apart. The outer 2 electrons are fixed in position. So basically, this electron here and this electron, number 1 and number 3, are somehow glued to the wall, if you will. And then the electron 2 in the middle between them kind of loose. It's free to go anywhere. All right. So they are set in this fashion. And now the question, first part of the question, he says, is the center electron, the one number 2, at a point of stable or unstable equilibrium? Okay. And part B said, if the center electron is displaced horizontally, say this way, by a small distance, okay, it's displaced horizontally by a small distance, what will its speed be when it is far away? There we go. You got that term again, very far away. What does that mean, very far away? Ignore potential. That's really the meaning of it. Okay, there is a voice should be in your head when you read that, very far away. Ignore the potential energy, because the potential depends on distance, 1 over r. This r now is very large, so it becomes an infinitesimal, so it's a small value. Okay, so he's asking what is the speed or the kinetic energy of the electron at far away. Got it? Okay, let's answer the first question. Let me make the drawing first. So what I have in here, so what I have is this diagram. Here is 1 electron, make them really big, nice and big. And they all 1 millimeter apart, like that. This is electron number 2, electron number 1, electron number 3. Okay? And we are assuming that electron number 1 and 3 are fixed in place. The free one is the electron number 2 is free to move. Okay, so that's basically the diagram for now. He says, is electron 2 is in stable equilibrium or unstable equilibrium? Well, okay. I'm sure a lot of you know the answer already, because I remember asking this question in class, in a regular one-to-one class, and most of the students will give me the right answer. So what's happening here? Let me talk a little bit about stable and unstable equilibrium. As you know, I'll put it here. The word equilibrium in physics means sum of the forces equal to 0. I can also add sum of the torque, sigma tau equals 0, and sigma force equals 0. That's basically the condition for equilibrium, is that all the forces sum up and you get 0. The equilibrium here has, there are two types of equilibrium. This is actually in advanced mechanics. One is called stable equilibrium, and the other one is unstable. I'm going to go over them very quickly, okay? Imagine I have, let's say, a hemisphere, say a bowl of cereal, okay? And the bowl of cereal is, let's say, it takes the shape of a hemisphere, half a sphere. Here it is. And I put a ball right in the center of it, right here. Okay, that's the ball. The ball is sitting there happy. It's not moving. It's right at the bottom, the very, very bottom of it, okay? And so now I can say that the ball here, the sphere here, is in equilibrium because the forces on it is 0. You see what I'm saying? And it is equilibrium at position, let's call it x0. Okay? Now what will happen if I slightly perturb the ball? The word perturb means slightly disturb. All right, in physics, we have a branch called Perturbation Theory. I'm trying to erase the darn thing. There we go. Okay, so what will happen if I slightly perturb it? In other words, let's say I give it a little kick, just a little kick. So what's going to happen to it? Well, it's going to start oscillating back and forth like that. Eventually, it will settle down, right? This is an example of a stable equilibrium. Okay, stable equilibrium means if I have a system in equilibrium where the forces on it, sigma F equals 0 and sigma tau equals 0, if I would perturb it, slightly disturb it, it would oscillate, shake, 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 and then it will settle down and go back or restore its condition, its old condition. It will be exactly the same old stable point right here at x0. You got that? Okay. Now, take the same situation, the same bowl of cereal, but this time I'm going to take the bowl of cereal and flip it like that. There it is. Now I'm going to put the ball here. Okay, now obviously, and the ball, of course, is at x0, you know, the equilibrium position. Now let me disturb it, perturb it, give it a little push or a little displacement. What's going to happen to it? It's not going to oscillate. What's going to happen is it's going to fall. It's going to immediately lose its stability, okay? Immediately. So that's an example of unstable equilibrium. This one is an example of stable equilibrium. Got it? That's the meaning. So stable equilibrium means when the system is perturbed, it will actually do what remember we talked about SHM. It is actually this oscillation that it's possessing here is 100% SHM, simple harmonic motion, and that SHM eventually will lead to it restoring its old position. Here, however, it's not going to oscillate at all. It's just going to fall. It will just go out of whack, and it will just be unstable. Okay. Now we come back to our situation here. As you can see here, so what's going on here? Look at the electron in the middle, the one that is sandwiched in between them. So they're all negative. So this electron 2 is suffering from repulsion from the electron 3. And it's also suffering from repulsion due to electron 1. Okay? Those two forces are equal to each other, exactly equal to each other. Okay, so what's going to happen? What's happening is that the electron is this electron 2, it's just sandwiched between them. It's just sitting there, but it's sitting like the situation of the ball at the top of the cereal bowl right here. The slightest perturbation will have it shoot in the opposite in one direction. So, for example, if I give it a displacement this way, it's going to shoot in this direction, like a gun. You see what I'm saying? And that's the subject of the second part of the problem. He says, go back to it. He said, if the center electron is displaced horizontally by a small distance, what will its speed be when it is far away? All right, so how does the picture look like? Let's see, let me take this one out. So at far away, the electron is here. Here is the electron. And this is going with some velocity. I'm going to call it v. The electron is going, it's shooting at this velocity. And I want to know the velocity of that electron. Okay? Again, we use conservation of energy. We ask the question simply, what is the total energy here of the electron before I disturb it, right? And what's the energy of the electron far away? And then those two energies must be equal. So while the electron is sitting here happy, before disturbance, there is no, trying to erase those. In this case, there is no kinetic energy, it's all potential. And this potential basically is before those two electrons. So let's calculate it. Let's say first the potential between 2 and 3 plus the potential between electron 2 and 1. At far away, well, there is no potential here. It's all kinetic, and it's just going to be 1/2 mv squared. This m here for the electron. You see what I'm saying? So let's calculate that. Keep in mind, because this is the potential energy, and it is not a vector quantity, the charge, if it's negative, you want to put that negative in there. If it's positive, you put positive, and so on. So you want to take that into consideration. However, because we're dealing with electrons, 2 electrons in each here, so it is negative times negative will give you a positive. Anyway, so what we have in here, let me write this on the here, 1/2 mev squared. I'll come back to it. And then for the potential between 2 and 3, that's going to be k e over r 2 and 3 plus k e, which is e squared. I should have said e squared, but anyway, 1 and 2. You see what I'm saying? And everything here is symmetric because r12, this is r23 right here, and this is r12, and they're all the same. So everything here really the same. So I can just add them up together, and that becomes this will become 2k e squared over r equals to 1/2 mve squared. Got that? And we can calculate all of this. Solving for VE, that will be equal to 4k e squared over rm. I hope I'm not messing it up, under the root. I think it's all right. And then we just calculate that. You see what I'm saying? And the answer in the book is 1,000 meters per second. Okay, let me do it very quickly. I'm just not. I don't know why I have the book doesn't. It doesn't look like my answer matches his. I mean the expression. Let me calculate. I still believe my answer is fine. 9 times 10 to the 9. The fundamental charge 1.602 times 10 to the negative 19 squared divided by the distance is 1 millimeter, which is 10 to the negative 3 times the mass of the electron, 9.11 times 10 to the negative 31, and then all of that under the root. You can calculate with me. Let me just go ahead and calculate right now. Let's see. Let's start with the 1.602 negative 19 squared times 9 times 4 divided by 9.11 negative 31 divided by negative 3, and then I'm going to take the square root of that, Answer, I got 1007. Definitely okay. All right. There we go. So I think the answer is fine. My answer is 1007 meters squared. He put it, that's the answer I got from here. Okay. And there we go. Okay. Okay, next. Okay, that's basically what I wanted to talk about as far as conservation of energy before we jump into a new topic in this chapter, and that's that is the electric potential or voltage. It's one of those abstract concepts that students have difficulty understanding, and teachers like me have difficulty explaining. So let's go into it. Okay, we have three words that mean the same thing. When we say the potential, without the word potential energy, without the word energy, the potential difference, and the third one, which is probably you've heard it a million times, the voltage. Okay, I like the word voltage for, you know, to replace all of them, but anyway, they have all the same meaning, and it has the symbol V, capital V. Okay, the voltage, or sometimes delta V. I'm a little bit goofy about the delta here. So if you see V, it could be delta V. But anyway, that's basically the difference, the symbol of it. What is it? Suppose I have a parallel plate capacitor. I want to explain it through that. Let's say I have a parallel plate capacitor here. There we go. Trying to erase it. I can't get it straight. Hold on. There we go. Okay, suppose this is positive. This is negative. And of course, as you know, there will be an electric field going from positive to negative like that. Here it is. Okay, suppose that I prepare this to be at a certain voltage. Okay, let's say the voltage is 12 volt. So the 12 volt will be at the positive plate, at the negative plate will be 0. Okay, 0 volt. You can actually do this experiment. Let's say you have a metal plate, separate them by some distance d, and then connect the positive terminal of the battery to this plate, and the negative to this plate, and then you have your voltmeter probe, and you move it, you know, in a straight line from the 12 to the 0. You will find that the voltage actually drops down linearly. In other words, what I mean by that is that if this is 12 and this is 0, right smack in the middle, it will be 6 volt, and right here it will be, say, 9 volt, and right here is going to be 3 volt, and so on. It is basically, there is a linear relationship between them, between the volt and the distance. Now the distance here, let's call it for simplicity d. Okay, and there is a relationship between the electric field that I have just talked about here and the voltage V and the distance, and that's this one. V equals E times D. Okay, got it? One way to remember it, Ed, you know, our friend Ed, that's how I remember it when I first learned this stuff. So the voltage is equal to ED. Okay, one more thing. Let's say I have, say, a proton situated here, okay? So let's say this proton, you know, let's say I'm holding it here, and I let go, and the proton, of course, we did that before, is going to shoot toward the negative plate, right? Here is my question. I would like to know what is the total energy of the proton right at this location, and let's say at this location right here. Okay, so I want to know the total energy of the proton here and here. Okay, let's assume that the distance from this, let's say I'm going to start measuring distances from the 12 volt plate right here. So let's say that this distance here, let's assume this distance is let's say 6 millimeters. Okay, so this is 1 millimeter. Okay, and here, however, let's suppose it is on the 5th millimeter mark. Got it? All right. So what is the total energy of the proton at the 1 millimeter mark? That's millimeter double M. Okay, 1 millimeter mark. What's the total energy of it? Well, the total energy is going to be K plus U, correct? Assuming that the proton started from 0, so let's say that the kinetic is 0. So we have just U. Well, what is U equal to? U is equal to QEX. I'm going to use X now, not D, because D is the separation distance. So what is X in this case? Again, since we're starting to measure from the 12 volt right here, so the X here is going to be 1 millimeter. Make sense? Let me call that X1. The electric field is, we'll assume the electric field is a uniform electric field, is constant. It doesn't change, okay? So that doesn't change. And then you have the charge on the proton, which is the fundamental charge. Okay. What about at the 5 millimeter mark? Well, at the 5 millimeter mark, the total energy is going to be, we do have kinetic, plus we do have also potential. The kinetic here is 1/2 mv squared, plus the potential, what is it? QE at x sub 2, where x sub 2, let me maybe call that x2, and this is x1, is the 5 millimeter mark. You see what I'm saying? Of course, those two equations are equal, so I can just go QE x1 must equal to 1/2 mv squared plus QE x2. You see what I'm saying? Now, notice here that we have just defined the voltage or the potential difference to be equal to electric field multiplied by the distance. Well, look at that. EX2, EX1. See that? So I can write this potential energy U, which is officially is equal to QED, is equal to QV or Q delta V. See what I'm saying? So that's a new definition. This is one way, another way of writing the potential energy, is that you can write it in terms of the voltage or the potential difference. So in this case, I can write this total energy is QV1 equals to 1/2 mv squared plus QV2. You see what I'm saying? So rather than using electric field and distances, I can, if I have a way of getting those voltages all through the distance between the two plates, I can just replace them and be able to get the potential energy. Okay. As a matter of fact, so you've probably seen the unit electron volt, EV, which is a unit of 1 electron volt is equal to 1.602 times 10 to the negative 19 joule. And that's the unit of energy, as you can see. And of course, this is the electric field right here. Excuse me, that's the charge E, which is the same as Q, the fundamental charge. So QV EV. You see what I'm saying? All right. I'm going to give you one example that talks exactly what I'm trying to say here, and that is example 25.6. I have two more examples from the book, and then we'll move on to the problems. 25.6. And that's on section 4. Let me go to the book. Section 4. How do I do section 4? the electric potential. Here's how we defined it. The potential is the potential difference. The voltage is the potential energy per unit charge. Okay, which is basically U equals QV. See that? There we go. And then one volt is 1 joule per second per coulomb, as you can see why, right? V is U over Q, so that makes it joule per coulomb. And I'm trying to find the problem. There it is right here. Okay, it says moving through a potential difference. Again, moving through voltage. That's what he's trying to say. Okay, he says a proton with speed 2 times 10 to the 5th meter per second enters a region of space in which there is an electric potential, in which there is a voltage. Okay, what is the proton's speed after it moves through a voltage of 100 volt? What will be the final speed if the proton is replaced by an electron? I'll let you do the second part. Got it? Okay, so how do we do it? Again, we want to use the constant of energy to do that. Let me show you a picture. He didn't draw any picture for this problem, even though this problem, you may have a problem solving it just because there is no picture. So I'm going to give you a little picture of it. This is just the way I visualize it. Imagine you have, again, positive and negative plate that look like this. Here's the negative plate. Here is the positive plate right here. This is the negative plate right there. And there is a hole, as you can see here. This is the hole right here. And then here is the proton coming. And it's going to enter the plates like that. Okay? And here it is the proton right here. The voltage between the plate is 100 volt. Okay, what does that mean? Well, it means this is 100 right here, and this is 0 right here. And he's asking, so here's a picture, okay? Now let's read the problem with this picture while we look at this picture. He says a proton going with a speed 200,000 meter per second, right there, enters a region of space right here between the plates in which there is an electric potential. All right, there is a voltage, 100. What's the proton's speed after it moves through the potential difference of 100? What will be its final speed if it was replaced by the electron? Got it? Okay. So how do we do it? Well, we would begin when we basically want to use the concept of conservation of energy. So I'm going to start my total energy right here the moment it enters the hole, and then the total energy here, I'm going to make them equal. Got it? Okay. Now here, right there, what is the total energy of the electron, of the proton? We have kinetic, obviously. Do we have potential? And the answer is no, for two reasons. Look, we said that the potential U, it's either QED or Q delta V, or V, okay? Well, the potential at the negative plate here, the potential is 0. The potential here is 100. So right at the hole right here, well, the voltage is 0, so there is no potential. That's one way to think about it. The second way to think about it is this, QED. E, in this case, is the electric field going this way. And D here is the distance traveled. Well, the electron, excuse me, the proton, I keep saying electron. The proton didn't travel any distance yet. So the distance here is 0. There is electric field, all right, but there is no distance. So that's 0. So either, I mean, both equations are very equivalent to each other. So whichever. But the one we are dealing with, of course, is this one, QV. Okay. So now, so at the negative plate right here, the total energy is nothing but kinetic. It's all kinetic. Okay? Right here, however, what we have kinetic plus potential. So there is kinetic plus potential. So that's going to be 1/2 mv squared. I mean, it's not the same kinetic, of course, as this one. Plus the potential. Well, what is the potential? Well, I can say E delta V, or EV, where V here is 100. You see what I'm saying? And E here is the charge, you know, QV. E here is the fundamental charge. Those two must be equal. So we equate them together. My pencil not doing well today. I don't know why. I'm trying to erase. 1/2 mv0 squared equals to 1/2 mv squared plus EV. And what is he asking for? He wants the velocity, right? Sorry, I forgot. What's the velocity? There we go. Just apply, you know, just solve for the velocity right here from here. So that's going to be 1/2 mv0 squared minus EV equals 1/2 mv squared. This is m over 2, so that's v squared equals to m over 2. 2 over m, that's going to be v0 squared minus 2ev over m under the root. You see what I'm saying? And then we just plug in our numbers and it should work out. You see what I'm saying? Everything is given to us. The V0, the voltage is 100, and this is the mass of the proton. Got it? And the answer, whoops, this is it's not V squared, that's just a V, right? So in this case, when you calculate all of that, he got for the proton 1.4 times 10 to the 5th. Whoops. I don't know what those lines, I keep seeing traces as I write, times 10 to the 5th. While I'm writing it, I just discovered a mistake. I hope some of you are screaming at me now for that mistake that I've made. And that is the potential here, it's moving. No, I think it's all right. No, this is the proton. I'm sorry. I was thinking of an electron. I don't know why. Yeah, if it's remember, if it's an electron, the E here becomes negative, right? That's a proton, so it's positive. So I think everything is okay. So I think this is fine. Okay. One more problem. And that is example 25.8. And then I would like to keep this video below 2 hours. .8. Let me just go to it. And that's in section 6. Again, this problem probably comes from nanotechnology. I'm not sure. It's not nuclear physics or anything like that. What is that? Example 25.7. One more. Whoops. Did I miss it? I'm going to pause the video. Okay, finally found it right here, 25.8, with this picture right here. Okay, he says, look at the picture as you read the problem. He says a proton is released from rest, so V0 equals 0, zero kinetic energy, at the surface of 1 centimeter diameter sphere that has been charged to 1000 volt. Okay, so we have a sphere here, 1000 volt. Of course, the proton is also positive. It doesn't want to be there, right? It's being repelled by it. So it can't, the moment you release your fingers off of it, it's going to shoot with large velocity, right? So he says, what is the charge of the sphere? Okay, given the voltage of the sphere, what is the associated charge? We'll come back, I'll tell you what that is. And B, what is the proton's speed 1 centimeter from the sphere? So when it is right here, 1 centimeter away. All right, so let's do this problem. Before I do that, I want to give you a quick idea about more ideas about voltage or the potential. So we said that the potential V is U over Q, correct? And we said that U is equal to K, Q, Q prime over R, right? Let's make this Q prime, okay? Q1, Q2 over R. Well, if I plug it into the potential formula, it becomes K, Q over R. See that? This is an expression for the potential, okay? What does that mean? It means the following. If I have a charge positive, Q, now at a certain distance R, say right here, this is a distance R, I know the electric field is equal to K, Q over R squared, right? This is the electric field at that point. The electric field is pointing out in the linear direction like that, right? I can also calculate the potential difference, the voltage, and that potential difference is equal to KQ over R. That potential. Now the difference between those two is what? The electric is a vector quantity, and it has a direction. Look at the radial direction, for example. The potential, however, is like, think of it like a potential energy. It's just a value at that point in space. Got it? So KQ over R. That's one thing. The second thing is voltage or potential is a scalar value. What that means, if the charge that you're dealing with is negative, you're going to put a negative right there. You see what I'm saying? So it becomes a negative potential difference. If it's positive, well, you put a positive. So because it's a scalar value, it's not a vector value, the charge, the sign of the charge becomes important, whether it has is it a negative potential or is it a positive potential? So this becomes important, okay? So make sure that you want to put the minus sign, if there is a minus, into the sign of the charge. Got it? Okay. Unless you want the absolute value, that's a different story. But that's basically what it is. So when do you use this? Well, dealing with a potential, with a particle or a ball or something, and you want to know what is the potential due to that charged particle at a certain point in space. Okay. So what he's saying in this problem is kind of similar to what we're talking about. Let me go back to it one more time. So what I have, he said a proton released from rest at the surface of a 1 centimeter diameter sphere that has B charged to 1000. Now he's asking, what is the charge on the sphere? Well, let's forget about the proton for a minute. Here is the sphere. Okay? And look at the charge here. He said positive 1000. See that plus? What does that mean? It means it's positively charged. In other words, this sphere is positively charged, like that. And the charge on it is some Q, that is positive, okay? And it has a radius, big R. And he said what the radius is. Didn't he give us this? Yeah, 1 centimeter diameter. So that makes it 0.5, right? Centimeter, okay? And he said the voltage is 1000 volt, the voltage on it. Well, he said, what is the charge? Well, I can just use this formula here. V, this formula right here. So V is equal to KQ over the radius, okay? Over the radius. So therefore, Q is equal to VR over K. See what I'm saying? And once we calculate that, so we have here 1000 times 0.5 times 10 to the negative 2 divided by K is 9 times 10 to the 9. And when we calculate that, I get 0.56, I'm copying it from the book, nanocoulomb. There we go. I don't know what this line right here, I don't know if you see it or not. I keep getting it. There is some wrong with the way I'm setting things here. I'm not sure what it is. If you know what it is, you can let me know. I would really appreciate it. I'm still learning about this OneNote thing. Anyway, all right. You got it so far? That's the easy part. The second part, part B, he says, what is the proton's speed at 1 centimeter from the sphere? In other words, let's go back to the picture. Here it is. Here is the picture. So we have the sphere here. It's 1000 volt. Here is the proton initially, right? And then I'll let go. So what's going to happen? The proton is going to shoot, and it is at a distance right at equal to the diameter of the sphere. What is the velocity here? Okay, assuming that the diameter of the sphere is 1 centimeter, and it is 1 centimeter away as well. Okay, so I want to know that. Okay, how do we do it? Well, all we need to do is to use conservation of energy. Okay, so we ask the question, what is the total energy before I release the proton, and what is the total energy at 1 centimeter away? And then I just equate them together. Okay. So right before I release the proton, how far is the proton from the sphere? Don't tell me 0. Remember, we measure things from their centers, right? So the distance right here, just like when I say, how far are you from the Earth? How far are you from the Earth? Don't tell me 0 because you're touching the Earth. You are 6 million meters away from the Earth, which is the center of the Earth. The radius of the Earth is 6 million. So you are, as you stand at the sea level, you are 6 million meters away from the center of the Earth. That's how far are you from the Earth. You get that? This is the same thing. You always measure from center to center. Okay. So here, for the potential energy before release, kinetic plus potential, well, there is no kinetic. All right. He said in the problem, it's from rest. Here. Proton released from rest. Kinetic 0. So equals to, here, however, it's moving all right. And it is not far away. He didn't say far away. He just said this 1 centimeter. He said 1 centimeter. So the diameter of 1 centimeter is just right here. So it's not far away. So you still have a significant potential there. Easy? Okay. So this becomes what? K, the potential. Charge on the proton. Charge on the sphere. We call it big Q. Over the radius of the sphere, which is ½ centimeter, equals to 1/2 m mass of the proton squared, right here, plus what? The potential. What's the potential here? Well, same formula. K E Q over R plus 1 centimeter. There we go. You can pause the video and think about it, but that's basically what it is. It's really easy. Okay? And then the rest is just algebra. Just solve for V. Okay, I'll fix the units, of course. R here is ½ centimeter, and it is 1 centimeter away. And you just work it out, work out the algebra, get it. The answer he got, 3.6 times 10 to the power of 5 meters per second. Okay, there we go. Okay. Okay, I think I am done with this chapter. I have 1, 2, maybe 3 problems, even though my throat started to hurt, but I'm going to finish them. I'm going to start, these are homework problems, I believe. I'm almost sure. I'm going to do problem number problem number 26. From the end of the chapter. (26). This one kind of a toughie problem. I get when I taught this course in the past, I get students coming to my office asking me about it. It's not really that bad, in my opinion. It's just, conservation of energy. Number 26. Right here. See the picture right there? Okay, he says he said a proton. He loves proton, doesn't he? There's so many particles out there. He keeps working with protons. Okay, he says a proton is fired with a speed of 200,000 meters per second. So here is a proton. It's fired to the right with a speed of 200,000. Of course, it's against this, we have here a positive plate, 500 volt. This is 0 volt. And of course, it's going against the field. You see what I'm saying? So eventually it's going to stop and then rebound to the negative. You see what I'm saying? Do you see the film in your head? Make sure you run the film in your head. You see the motion of this proton. Okay, so here a proton is fired with a speed of 200,000 from midpoint of the capacitor toward the positive plate. Show that this is insufficient speed to reach the positive plate. Interesting. This is insufficient speed. In other words, it is similar to, I have a stone in my hand, I am standing on the ground, and I throw the stone up in the air, and I want to show to myself that the speed that is, the speed of the stone is not sufficient to make the stone escape from the gravitational pull of the Earth. That's exactly what you have in there. So basically, the proton is going to reach a certain quote-unquote altitude, and then rebound and fall back to the negative plate. You got that? That's the story that we have here. How do I do that? How do I do that mathematically to show that this is insufficient speed? Okay. Well, the condition for insufficient speed is that, before, I hate to give you a free answer like that. Let me tell you this. If the kinetic energy of the proton is greater than the gravitational energy, what will happen? And the converse, if the gravitational energy is greater than the kinetic, what will happen? Well, let me draw it. So here is what I have. This is the positive plate right here. Negative. And this is 500 volt. We'll come to that 500 in a minute. 0 volt. Here is midway right there. So remember I told you it's linear. So that means without the problem telling you that, you know this is 250 volt because it's midway. And then I have the proton is like this. And what's going to happen? I shoot the proton like that, and it's going to go, it's going to reach a certain altitude, and it's going to fall back like that. That's basically the story. Got it? And this is the initial velocity. Okay? That's basically the picture that we have. Now, he said, show it is insufficient. So the condition, if I call this position 1, this is position 2, and this is position 3. We're going to come back to position 3 in the second part of the problem. Okay? So the energy in 1, total, in position 1, how do I do that? Here, 1. Is that okay like that? What an ugly notation, but anyway, it's all right. So what do we have in here? Well, it's going to be K plus U, so that's going to be 1/2 mv0 squared plus EV. Is that all right? V here, of course, is what? 250. This is the position in 1 right here, the total energy. Okay? All right. What about the total energy in 2? You know, I'm going to drop that T. I don't need it. Because when I put that circle 1, it's obvious that it's total energy. Okay, so now, what is the total energy at 2? Well, the total energy at 2 is just the voltage, the 500. This one right there. So the total energy here is EV, and that's where V here is 500. You see what I'm saying? Let me calculate both of them. That's 1/2 mv squared. Remember, I have that. That's going to be there. So that's going to be 1/2. The mass of the proton, 1.67 times 10 to the negative 27, multiplied by the velocity, 2 times 10 to the 5th, all given to us, plus EV, right? So the charge 1.602 times 10 to the negative 19 times the voltage 250 volt. Now you calculate all of that, okay? I did the calculation and I got, okay, the first part right here, and right here. The first part, I got 3.34 times 10 to the negative 17, and the second part, I got 4 times 10 to the negative 17. You add them up together, you will get 7.34 times 10 to the negative 17 joule. This is the total energy. This is the total energy of the proton at position 1, midway, before, right at the moment when I shot it, right here. What's the total energy right here? Well, it got kinetic, 1/2 mv0 squared, plus that potential, the voltage, EV, here, 250. See what I'm saying? And there we go, I got that. There is the total energy of the electron. Let me calculate the total energy of the electron at position 2, if it was at position 2, where it's going to stop right there. So at E sub 2, it's just going to be EV, and that's 1.602 times 10 to the negative 19 times 500, right? And that's equal to what? 8.01 times 10 to the negative 17 joule. Now compare E1 with E2. You notice that E1 is less than E2. In other words, it's not sufficient energy. Not sufficient. To reach. It has to be larger than that to reach it. You see what I'm saying? To reach positive plate, that is. Okay? Another way of seeing it, this is one way to see it, okay? Another way of seeing it, look at that. Let me change the color. Remember I told you about bound orbit and unbound, and it has to do with the kinetic and potential? Look at that. When we calculated this one, which came from this one here, right? This is kinetic, this is potential, so that's kinetic right here, and that's potential. Which one is greater? Look at that, kinetic is less than potential here, within it, okay? That's another way of saying that it's not enough. It's just not enough. You see what I'm saying? That's another way of saying it. So here we say EV is less than 1/2 mv0 squared to reach the positive plate. Got it? Okay. Second part. He said, what is the proton's speed as it collides with the negative plate right here? All right, so basically, let's go back to the picture. I want to know the velocity right here. All right? Again, you can use conservation of energy. Conservation of energy of what? Well, you know, pick any one of them. You can pick position 2 with 3 or 1 with 3. Since I know a lot about 1, so I'm going to equate total energy at 1 and total energy at 3 to get V. You see the plan? So I can go like this. Part B. So here I have at E3, okay? What is the total energy at 3? Let's go back to the picture. Do I have potential here? Do I have potential? Look at the circle. No. See that? There is no potential because the potential energy, that is, sorry. There is no potential energy because the potential, the voltage is 0 here. But I do have kinetic, okay? So all E3 is really all kinetic. So here I have E3, it is K plus U, but U is 0. So that's just 1/2 mv squared. And of course, E sub 1 is what we have just written, 1/2 mv0 squared plus EV, we can equate those two together and solve for V. So in this case, I will have 1/2 mv squared equals to 1/2 mv0 squared plus EV. And we got that. This part right here is basically this part right here. See that? E1. 7.3, 7.34, negative 17. So that's 7.34 times 10 to the negative 17 equals to 1/2 the mass, 1.67 times 10 to the negative 27 v squared. And then you work it out. And I'm looking at my notes. My answer is 2.965 times 10 to the power of 5 meter per second. There we go. Whoop. There we go. Okay. Good. One more. If you go back to the problems, for those of you who wants to work a little bit more on problems, because my background is in nuclear and particle physics, I like those kind of problems and I enjoy solving them. Starting from problem number 56, right here, 56, 57, 58, and 59. Okay, these are all particle physics problems. I like to work on them. I'm not going to do all of them in class here, but I'll pick maybe a couple of them. Let me do number 57 and 50. Let's see, 58. I'll do 57. Okay, for now. Yeah, let me do 57. You know what? I'll do 56 and 57. That's it. We'll call it a day. Okay? 56 and 57. Let's start with 56. They're both not bad. They're very interesting, though. Again, those books, those problems, you can actually find them in a typical nuclear physics book. They're very realistic. All right. It says a proton is fired from far away. There we go, this word again. A proton is fired from far away toward the nucleus of an iron atom. Okay, the iron. Now, the iron atom has 26 protons. Okay, so the iron element number is 26. So it's a huge, very, very large compared to one proton. So it has 26 protons and a diameter of 9 femtometer. The femto is 10 to the negative 15. What initial speed does the proton need to just reach the surface of the nucleus? Okay, we just did this problem with the glass sphere, remember? Assume the nucleus remains at rest. In a nuclear physics book, definitely you're not going to assume that because you're not going to get the right answer. You have to take into account the recoil. It's called the recoil of the nucleus, of the target particle. But for this course, we're not going to take that. It becomes a little bit more complicated. You have to use, you have to incorporate momentum into it and the center of mass system. Anyway, so how do we do this problem? Okay. Number 56. So I'll do it quickly. So what I have here is the iron Fe26, and here's the line of action, if you will. Here is the proton from far away, right? And what's going to happen is that, let me read it again, I'm sorry. The proton is fired from far toward the nucleus, item the iron is, okay. What initial speed does the proton need to reach the surface of the nucleus? So we want it to just reach the surface and rebound. It's very similar to the glass problem. Maybe I should have done it. It's a very easy problem, really. I hope it is. Just like that, right? So from far away, that means the total energy here is just 1/2 mv0 squared. at the distance of closest approach right here, what would it be? Well, it's all potential because it's going to stop and then rebound. So it's going to stop. There's no kinetic. It's all potential. So in this case, it's going to be K E, the charge of the proton, times 26e, the charge of the iron nucleus, divided by how far are they from each other? Well, it's just the radius of the iron nucleus, which is given to us. He said 9 femtos, so that's 9 times 10 to the negative 15. Is that right? And that's it. We just calculate that, and you calculate the velocity of that. Got it? Okay. Number 57, similar kind of, but it has a little twist to it. Okay, 57. Whoa, it's level 3. Why? Is it that bad? Yeah, it is level 3. Okay, he said a proton is fired from far away toward the nucleus of a mercury atom. The mercury has element number, which is the number of protons in it, is 80. And the diameter is 14 femtometer, so that's a larger nucleus. If the proton is fired with a speed of 40 million meters per second, okay? 40 million meters per second. What is the closest approach to the surface of the nucleus? Okay? All right, here's what happens. So I have here is the mercury nucleus. It is 80. The charge on it is 80e, if you will. And he gives me the diameter, or excuse me, is it the radius or the diameter, whatever it is. And then here is the proton is fired with velocity v naught given to us, right? And what's going to happen is this, guys. What's going to happen is that the proton is going to shoot towards it. It's going to reach a certain point, and it's going to rebound like that, okay? This distance from the center of the nucleus to where the proton reaches, in nuclear physics is called the DCA. If I can draw it better. DCA, the distance of closest approach, the DCA, okay? So, as he's asking for, what is the DCA, all right? These are the typical problem that you do in nuclear physics where you want to reach a certain DCA for other reason. There is a reason why they do it. They don't want to bombard. See, if you would shoot the proton in it, you could not destroy, you would actually split and become into 2 elements, or the proton becomes absorbed in it and it will change the identity of this nucleus. But sometimes you want to shoot it and up to a certain distance, as it's called the DCA, for a good reason. Anyway, so what is that DCA? How do I determine that? Again, we can use conservation of energy. So he says a proton is fired from far away, which means there is no potential here. So right here, the energy is right here. When I point with the pen, it doesn't show. I have to point with the mouse. There we go. So right here, the energy E is equal to 1/2 mv naught squared. Okay? This is far away. Far away. All right. Now at the DCA, well, what's going on? Is the proton moving? It just stopped before it rebounded, right? Stopped right here. So the total energy here is nothing but U, and that's going to be K E times 80E, right? Divided by how far is it? Well, it is DCA. And the DCA is measured from the moment the proton stopped all the way to the center of the mercury. Got it? Now, he's asking, I think he's asking a different question. Let me read it again. I'm sorry. He said, if the proton is fired this speed, what is the closest approach to the surface? Okay? So what we're doing now, we're just doing the DCA. That's okay. We didn't do this problem. Basically, we want to subtract the radius. Anyway, So let's continue on. So we have that. I'm going to equate them together. So in this case, I'll have 1/2 m v0 squared equals to k80 e squared over dca, and then I'm going to solve for the dca. So that will be 80 e squared k times 2. I'm doing the algebra and trying to do it in one step. V squared. There we go. Is that right? And then you just calculate all of that. And then you calculate the dca. I don't have an answer for it. You do it, please. Once you get that, he says, how far is it from the surface? He said the diameter is 14. Okay, so the diameter here is 14 right here. That means the radius from here to here is 7 femtometer. I got the dca from here to there, so he wants the distance this. I'm sure you can do it easy, right? Okay, let me go back to 56. I'm done basically with what I want to talk about today. 56, he gives you the diameter of the nucleus is 9 femto. I think I used it as radius. Yes, I have, right? I'm sorry about that. He said, I misunderstood. I thought the radius is 9 femto. So this is 9 femtometers here, right? So the radius in this case is going to be 4.5. I beg your pardon. So that's going to be 4.5 right there. Like that. Got it? Okay. And that's it. Okay. Have a good week. Bye-bye.